Hi, we're going to look at parallel circuitry of resistors. Again, we're going to use the light bulb as a resistor over here. So let's get started. We're going to need a battery. We're going to need a couple of wires and a switch and three light bulbs. So I'm going to just pull these out. We'll attach some ammeters as well. Right, we'll be needing three. We're gonna take uh, this later. Now we need a lot of wires, right? Okay, there we go. Okay, now to begin the circuitry, I'm going to create a junction through which I'm able to divide this circuit into a parallel combination. Yes, over here, bulb number 1. Now let me connect bulb number 2 like this, and now we have bulb number 3 right over here. Now it may seem a little bit small to you. I will zoom it up to give you individual component wise detail, but let's just put these out, and I'm going to connect this ammeter to all three of them, right? So please don't mind the shape of the circuitry. It's the same as that. I'll give an illustration as well along with it. So let's connect this. One connection, second connection, and there we go with the third one, right? Now this is by and large a parallel combination of three resistors, right? Now I'm going to need another ammeter to work my way and see what total amount of current is being drawn by the circuitry. Now this is a parallel combination of the circuit, right? Let me just move this a little bit down so that we can all see this better. Okay, there we have it. Now I'm going to use conventional current as a start, and I'll keep the values on so that you know what are the values available for the devices. Now since the switch is on, so no current is flowing through the circuitry. As soon as I turn on the switch, as you can see, now the current starts flowing through the circuitry and the bulbs will glow up, right? And we can now see the value for the currents, right? Now let's take out a voltmeter and let's check the potential across these 2 points, right? Point A and point B over here, right? This is point A, which is the point where the current is being divided into 3, and this is the other point, right? Oh, negative terminals, right? There you go. Now as you can see that the voltage across all 3 bulbs is 9 volts, but if I check the individual voltages for each bulb, it is again 9 volts. That means that the voltage is equally divided by this point over here, right? So this point we call as a junction. A junction is a point through which several connections are coming out, and they have the equal status in terms of voltages, right? As you can see, the voltage, if I put it to the junction and check individual voltages through each bulb, it's the same, right? And that is the same for this terminal over here, and even for the other end of the circuitry. So in parallel combination, the voltage remains constant, right? It is equal to the supplied voltage, and it's the same for all 3 combinations, or all 3 devices in the combination, of resistors in this case, right? And the current, however, is actually the sum of what we have in the circuitry is equal to this 3 individual currents, right? So as you can see, the speed of the current over here is fast. From this junction, the current is now dividing into 3 equal parts. Now this is why this is equal, because the resistances are equal. Now if we change the resistance of one circuit, right, let's just make it half, right? Okay, as you can see, now over here the current is going a little faster, and if I make this one having more twice the resistance, now you can see that the currents are entirely different for each of these. Since the resistances are different, The one with less resistance will have more current going through it. The one with more resistance will have less current going through it, and the one with most resistance will have the least current going through it. As you can see, the bulb with 5 ohm resistance is glowing the brightest, 10 ohm is glowing a little less, and 20 is least intense in terms of light, right? And you can also look at the currents that are going through it. So the 1.8 amperes are going through this, zero point 0.9 from this, 0.45 amperes from this circuit, and now this is all adding up to 3.15 amperes, which is the sum of all these three individual currents. So over here we can safely say that the current is the sum of all three currents going through each device, which is equal to the total current in the circuitry that is flowing. As you can see, all these three are adding up together. These arrows are mixing up and the speed is increasing. This is just a representation. This is obviously the speeds do not really change that well. It's just the resistance and the amount of current that flows, but this is just an animation, so it's very good display of how the currents are different because of these three differences in the resistances, right? Now when we talk about, now let me just make the same value for all three so that all three of them are glowing at the same intensity and offering same path for the current, right? Now remember, over here I would signify this point that current prefers to go, more current will flow through a lesser resistance, right? So over here we can say that current prefers to go through a path of low resistance, right? First, so the more current will flow through low resistance, right? Now since the resistance are same, now you can see that it is same for all three connections over here and over here as well, right? And with, even if I change the resistance, let's say this was 5, right? Previously it was 5, okay, and this we made 20, right? So let's make it to 20 ohms. Now even if I check the voltages for these individual bulbs, it's 9, 9 and 9, even though the current is different, but the voltage will remain the same since this is parallel combination, right? So in parallel combination, the voltage will remain same across the devices and it is equal to the applied or the supplied voltage, right? While the current will be different for all three parts of the circuit, right? So we can safely say that the total current is the sum of the currents, and the resistance over here is actually the inverse sum of all these three resistances, right? Now as soon as I break off a part of the circuit, as you can see, the current has slowed down. Why? Because now current only has to go through the path of higher resistances, since the path of low resistance is now open, right? Now if I further remove another combination part, right, you can see now the current is even slower, because now current can only and only go through this one bulb, which is offering higher resistance. So the total amount of current is actually dropping down. Although on the contrary, this is actually supposed to go up in common sense, but again, science not always just think about common sense. It's mathematical application. So mathematically speaking, since this is the resistance was an inverse summation of individual resistances, right, as you can see at the bottom, we can surely say that by removing these paths, the equivalent resistance will go up, right? The more resistance we add in terms of parallel combination, the lesser the equivalent resistance is, right? Now with all three bulbs, there is more current flowing through the circuitry, and if I remove these paths or break off these paths, you can see the current is dropping dramatically, right? So we can surely say that the resistance over here is an inverse sum of these individual values. So the equivalent resistance is definitely far less than the individual resistors. It would be lower than any of these individual resistors, the equivalent resistance, right? Hope to see you with next videos. We'll post those and share those. If you have any questions, please put it in the comments, or put up a video and share with me, share the link, and I'll try to respond as soon as possible. Thank you.